Hi everyone, I'm back again. Okay, this video is entitled Magnetic Conduction. Been asked a few questions and they all kind of fall into the same sort of category, so I decided to throw them all together in one video and just throw it at you. Should warn you that some of this stuff I've made it easier for beginners to understand what's going on, again, which means it's not entirely technically accurate, but I made it simple for people to understand. I should also point out, after my last video, be careful when playing with magnets. Much to the amusement of other people, Angus, they can hurt and cause injury, so just be careful when playing with them, especially high strength neodymiums. Okay, first example, what happens when you stack a magnet, and what happens to the field when it flows from the north side of one magnet into the south side of the other. So as you can see, one magnet, two magnets, there's a north field, there's a south field. It is, believe it or not, relatively simple. Right. So we'll start from the north side of the first magnet. Yes, this is a reused piece of paper, by the way. Flux lines, literally, can you see them? Just about. Yes, a sharpened pencil, by the way. Can you see them? You can when I stick my head over the light. That's weird. Okay, let's draw them a bit heavier. There you go, that's better. They literally shoot across north-south between the two magnets. It's the same if they were butted straight up to each other or whether there's a gap, the fields go straight across. There is a very little bit of field that does come round, but it's negligible. There's always going to be a little bit that loops around. What happens this magnet? Well, again, you have a little bit that sneaks back round, but ultimately it does that. And is that the middle? One more. Moves around like that. Same thing there on the other side. Not on camera, behave. So simple enough. Some people would expect that to be the answer. What can I say? If you have a gap in the middle, right, you have a different bubble around it than if you had the two magnets butted up to each other. Slightly larger, etc. You can use that to your advantage depending on what you're doing with a motor, because you've artificially enhanced or expanded the bubble. So that should be relatively simple. Now, magnetic conduction. Yep, I've been prepared for this video, and I've just turned this piece of paper over, by the way. Here, reused. Right, magnet, and here we have a piece of iron. Assume it's a solid piece of iron. We'll make it easy to start with. Okay. Simply put, the piece of iron is a conductor of the magnetic field. Now, none of the magnetic field is ever lost through conduction. However, its effects diminish throughout the length. Why? That's a good question. Okay, first of all, we need to start with the makeup of basically a ferrous material. That is something that is attracted to a magnetic field and will conduct it down its length. Putting it in simple terms without going too heavily into chemistry, each metal or material is made up of, well, you've got all sorts of elements in the periodic table that you can pick from. You've got mixtures of elements, etc., for X, Y and Z purposes. That gets complicated, so we're going to stick with iron. Iron is an element. In a chunk of iron, right, there is, well, in a pure chunk of iron anyway, there is no other element present. There is just iron. As I keep saying to people, steel is not iron. It is made up of somewhere in the region of 80% iron, but it is not iron. Right, so we're going to completely ignore steel for the time being. Okay, so we have here a virtual chunk of iron. Looks a bit like what you'd see from your generator cores, wouldn't it? Didn't do that by accident. Okay, so down at the bottom of the page, we're going to do an exploded view. Real close-up view of what iron is. Now, in its natural form, it has what's often described as ions. Strangely enough, it's no coincidence. Iron is IORN, whereas iron is ION. That's going to confuse you. Okay, I refer to the element as the element iron, and the ions as in what I'm going to refer to as crystals, Okay, which is more, in terms of chemistry, it's more accurate. So, inside your chunk of iron, you have crystals, which are clumps of the iron element in a specific pattern, putting it simply. So like you have various patterns like oh, mine's gone blank. Like you would have a square pattern, one on top of each other, or you'd have triangles, squares, pentagons, hexagons, octagons, decahedrons, etc. That's how the crystals are within each chunk of the iron element. Because it's not all uniform. Unless you specifically engineer the material, even if it's just an element such as iron, right, the crystals are going to be all over the place. Right. So, basically, putting them so that you can understand, it's not necessarily how the shapes actually are, but we're going to draw them as ellipses. And you can just about see that, I think. Let's draw it in a bit like that. And guess what? They're not aligned. So you'll have another one like that, one like that, and they can also be different sizes as well, strangely enough. You get the idea. They're just not aligned, they're all over the place. You'd think they would be nice and symmetrical. Not gonna happen. Not in a natural form anyway. So let's take a look at one up close. Simply put, it's kind of like that. Now, each one of these crystals has a shall we say, a magnetic centre line. In this case, just so I can actually draw a straight line. Hey, I got it in the centre. Cool. Right, that's the magnetic centre line. Okay. The magnetic field likes to flow up that centre line. We'll talk about that towards the end. Okay. In the actual element itself, because these are all over the place, there is no natural magnetic field, because this one hits that one and blocks it, and it goes this way, and that one will hit something else and send it off another way, and basically it just scatters the field all over the place. Right. In a ferrous material, here, this bit's fun. Right. In a ferrous material, the crystals will actually, magnetically speaking, align with each other. So, like here, magnet, chunk of iron, right, the crystals will sort of, it's a soft alignment, means it's not permanent. Right. They sort of align in the same kind of direction. Can you see that? No, you can. Now, they don't perfectly align, right? And there is a reason for that. Basically, you're making the crystal switch from its natural form to an aligned form, but once you remove the magnetic field, it'll go back again, but it doesn't perfectly align. Simple explanation purposes, it's elastic. You know, it tries to align around with the direction of the field, but there's a piece of elastic pulling it back, so it doesn't fully align. So on these, do it by hand. You've got fields that go that way, ones that go that way, and in total you end up getting a rough direction of that way. Rough direction. I'll explain that in a minute, I'll come to it, just bear with me. Right, so in a magnet here, right, provided the chunk of iron is thick enough, right, what you will get is a compression of the magnetic field into the chunk of iron, right, from the magnet. Assuming the magnet is bigger than the chunk of iron, of course, you will get a compression. It will drag the field in. Right, I'm going to have to, everyone remember that bit? And that, right, it's gone. I need to scrub it out. No, actually I could have left it. Un momento. Ooh, that's just made a mess of my rubber. There we go. Right. Now, simply put, as I said, the magnetic field, or the magnetic flux, is conducted up the length of the iron. However, let's get to the end, it doesn't all come out at the end. Where does it go? You've got it. It does this. Right. As I said in the last video, the magnetic field will follow the path of least resistance. Same as voltage. So it's also affected by the density of the magnetic field. So packing it into a small area, right, it wants to expand back out again and sort of have a natural gradient to it. Doesn't like being compact into a small area. Generally tends to have an explosive effect, so to speak. So what actually happens is, I'll draw it on this side for you. Basically it will come round like that. So all the way up this core, it will come out from the sides and go back. Like that. And so on and so forth, all the way up to the end, where you get a little bit that eventually flows all the way around and back. Like that. Hopefully you can see where I'm going. Comes out little bits, all the way up its length. Simple reason being that yes, it likes the conductor, right, but it wants to find the path of least resistance, as I said. This area becomes a, magnetically speaking, void, right, so it can hop back and back around relatively easy. The next one, it likes to be a nice gradient, as in the spacing this way up the side of the magnet. So easiest route is a curve round, simply put. Now another question that had been asked indirectly is, why does a magnetic field attract? Well, that's a very good question, and it's not one that's easily answered. Excuse my hand being right in front of the camera. Yes, my camera's sat on top of my keyboard, so it has a close-up view of what I'm trying to draw for you. As I said, why does a magnet attract things? Truth be known, the top scientists are well, the last time I looked into it, they are undecided as a whole, collectively. That's the top guys. You know, the guys that got huge numbers of PhDs and degrees and more letters after the name than are in the name. That's the last time I checked. Now, there are two groups. There may be more, but oh bugger. But there's only two groups of scientists that I'm aware of. One is the quantum physics group, and the other one is the string theory group. Now this is going quite heavily. Ultimately, the two sort of theories around the universe, so to speak. Quantum physics says that a magnet must have particles emanating from one side and going into the other, which we know isn't true because we don't see them and can't prove they exist. But we can prove that a magnet has a force. Now the string theory group is quite difficult to explain, but it does have, there is an explanation for it that does explain attraction and repulsion. Right, now, if you want string theory explained and quantum physics explained, I'll tell you what the videos are at the end, but I'm going to link into a video that explains in English what the two are, because it does it way better than I can. So I'll cross-link you that video. However, it does go quite in depth. Also, another reason for this video, I've just reminded myself. I've had a message from a user, I'm not going to name him, who has challenged my explanation on magnetic fields, and says, basically he said, how do you know that those gust lines exist? Well, two reasons for these videos. Number one, practical knowledge of magnets. I've played with magnets so much, done experiments, etc, etc, to the point where I physically know how a magnet's going to behave, how it's going to react. On top of that, I've read quite a bit of literature on it. So I've got practical experience, but as he was quite right to challenge me on it, I linked him a load of YouTube videos on the subject, and as a result I have yet to have a message back from him. So one of the videos that covers the quantum universe and the string theory also shows the gust lines. The pictures that are on there are for more advanced, to do with conductors, but as per my last video, if you've looked up the left and right hand rules, you'll know that a magnetic field surrounds a wire. So the gust lines that are shown there around two wires, here, that's the fun bit, you can just assume that one of those wires is a magnet, right? So on and so forth. So it does explain, but ultimately, as I say to everyone, don't take my word for it, go and experiment yourself, go and look it up. Simple experiment, magnet, iron filings, piece of paper, that's all you need to do. Magnet underneath clean sheet of paper, pour some iron filings on the top, and what you'll find is the iron filings, right, will stand up, right, and form basically stalactites up from the magnet, from the pole of the magnet, right? But the thing is, they will follow the gust lines. So what you will see, if you can get them to grow big enough without collapsing in on themselves, right, you will actually see them start to bend outwards like a flower. Ergo, proves my point. So, don't take my word for it, go and do it yourself. Right, so, going way back to magnetic attraction. How can I explain it in simple terms? Because the beginners may not understand, even though it's been explained quite simply, they may not understand the quantum theories and the string theories on this. So I'm going to explain it in a known manner that is consistent with the behaviour of a magnet. Well, we know the behaviour of the magnet. It likes to hurt and maim. Yeah, joking aside here. Okay, we know that the flux lines from the north are attracted to the magnetically conductive material. Darn it, I drank my coffee. Seriously. Right. So what happens is it compresses it. It drags it in, it sucks it in because it's conductive. So think of lanes on a highway. Right. If you go from, say, 4 lanes to 2, right, it's logical to say that the traffic on the 2 lanes have to travel twice as fast as the traffic on the 4 lanes just to keep the flow going. Right? And that's kind of what happens here. This is the only way I can explain it. Right? It sucks it in because it travels so fast along here. Right? So it literally sucks it. Right? And because this is travelling so fast, drawing it out, so to speak, right, it creates a difference in magnetic pressure. Right? Because the magnetic fields always want to travel the shortest distance round. Because you've got this gap here, it wants to pull it in to make the gap shorter, so it can travel around faster. Less distance to travel. We like that. So it pulls it in, and hey presto, that's where the force comes from. It's the only way I can describe it is a pressure difference in terms that beginners can understand. And my God, you can tell I've reused that piece of paper a few times. That's the only way I can describe it. Now, practical experience of magnets, yeah, in theory, we'll do it this way. That's probably the best way I can describe this. Oh my God, I think this piece of paper has kind of had it now. I might turn it into a paper aeroplane. Yeah, get one final use out of it. That is really grubby. Okay, in theory, if you sat, we'll assume that friction does not apply. That's going to look weird. Yeah, thought it would. In theory, and you see that, yeah, it's not too bad. Now you can see it. Oh my God. Definitely need a new sheet. Right. In theory, if this material here could be made to be magnetically isolative, right, so it does not conduct a magnetic field and it does not allow a magnetic field to pass through it, right, what would happen here is a build-up of magnetic field, putting it in simple terms, which creates a pressure difference, again simple terms, and it would push the magnet up the tube and out, right? As if this vessel was a magnet itself. So this magnet, if this material was magnetically insulative, right, it does not allow the magnetic field to conduct through it, nor does it allow it to pass through it, right, then this section behind the magnet would become virtually magnetic. You build up a magnetic pressure behind it equal to the field from the magnet itself and repulse the magnet. Don't ask me how to do that. It goes into a level of chemistry that I've got no chance in hell of explaining. But we know a magnetic field can be conductive, so in theory, why can't we create something that's insulative? Now at that point, either people's heads will explode, or they'll explode anyway because their imagination will start running wild. Being able to conduct a magnetic field, being able to insulate it. Don't forget, you have also got a third state where a magnetic field will just pass through an object unrestricted in whichever way it wants. That is non-ferrous materials. Now we already know the favourite experiments with lens field down a copper tube. Yeah, this sheet's had it. We already know that produces a lens field which stops it. But that is due to the magnetic flux lines intersecting with the copper, but because they are moving, it turns the copper into a short circuit, basically. So it's a micro short circuit coil which creates a lens field in the opposite direction, thus dragging the magnet. We know that it's been featured many times on many videos on YouTube. It's similar type of principle. So if you pass a magnet down something electrically conductive, then you will most likely get a lens field. Doesn't matter whether it's iron, aluminium, copper, brass, mercury, many other conductive materials, you will still get a lens field. Right, so another example, two magnets 90 degrees of rotation apart, north to south. Guess what? You get a little bit of separation there, you get a little bit there, a little bit there, and a little bit there that will always flow round. It's always there, just accept it. Now, what will happen here is the gust lines curve round like that. But it's not exactly a perfect semicircle. I can't draw. Oh, it's not exactly perfect. What will happen is a slight compression halfway between the two magnets, orientation wise. There's a slight compression there. Right, so the field at this point will be slightly shorter than the diameter of the magnets. Right. What happens on the back side? Well, let's position this so you can actually see. It basically goes from here round to there. So you kind of get a weird rainbow effect. Actually got it right. Now, just with here, I said you get a slight compression in the field. Here you get the opposite. It flares out a bit. So those two types you can use to your advantage for generator coils. Right. Where it flares out on the backside, probably not going to be able to use that too much. But where it compresses, right, that means you get more magnetic field in a smaller space, which is a good thing, because if you engineer your rotors right for generation, then you basically have more magnetic field in a smaller space, which you could then channel through a coil. Excuse me. So for example, if you had two magnets like that and you spun a rotor, just to give you an idea here, there you go. If you spun a rotor on that plane vertically as it comes up from the page, right, with coils on, yeah, so you're passing the coils through this field, right? Yes, it's a G-field generator, but more importantly, it's a denser magnetic field. Ergo, you get more output. By the same token, you also get more lens. So you have to work that out as well. So hopefully all of that will make sense to people. Oh, before I forget, the videos that I'm going to put up, there's 3 of them in total. The first 2 are about how magnets are made. Basically, the very first one is an older video done in the 90s, I think it is. It's from the How It's Made series. It's about 5 minutes long, I think, and it's an older type, but it's still good. It shows making a few magnets, and not all the processes, but most of them that go through how to make a magnet. Second one is reasonably recent. It's by a company that makes magnets to various specifications. Not all of the processes are shown, probably because they don't want it to get out. So that's the second one. Third one, as I've mentioned, will be the explanation of the magnetic field. Parts of it back up things that I've already told you. Other parts are probably going to be way beyond what beginners can understand properly, at least anyway. And that is the stuff on the quantum field theory and the string field theory. Which one's right, which one's wrong, God knows. I have no idea. Your guess is as good as mine on that one, probably. But anyway, this video is like 39 minutes long, and it's got to be the longest one I've done so far. So the next video, not quite sure where it'll be. Depends on what questions I get asked and when. I know Mr. Angus has a question pending for me to answer. I'm just waiting for him to get back to me with some information. And I'll see if I can do a video to explain it in simple terms for everyone. But as always, any questions, give me a holler. Okay, have fun. Remember, whatever you do, don't hurt yourself with magnets. They do sting, trust me. The first time you do it with a strong neodymium magnet, it's quite painful. It's a unique pain as well. You know, I don't advise it, so be careful. Yeah, any questions, give me a holler. Talk to you later.